Welcome, everyone. Today, we are moving beyond basic step-by-step AI reasoning. We are exploring recursive chain of thought mastery. You will learn how to build advanced loops where Claude actively analyzes, critiques, and refines its own reasoning path to eliminate logical inconsistencies. Let us get started. Let us introduce the concept of recursive chain of thought, or RCOT. Standard chain of thought simply asks Claude to think step by step. However, recursive chain of thought is much more advanced. It is a technique where the AI builds layers of analysis that continuously reference and refine each other. The basics involve forcing the AI to stop, turn around, and aggressively interrogate its own previous reasoning steps. Why do we do this? Because LLMs are prone to first-answer bias. If they make a slight logical error in step 1, they will confidently hallucinate an entire strategy based on that flawed premise. How do we fix this? We instruct Claude to question its own assumptions across multiple, distinct levels. In our deep dive, we see that by forcing Claude to generate a textual critique of its own work, its internal attention mechanism must process those flaws. This effectively rewires the mathematical trajectory of its final output, leading to vastly superior logic. Look at this comparison in our flowchart. The top path shows standard chain of thought, a linear progression from step 1 to step 2, directly to the final answer. But look at the bottom path, the recursive chain of thought. After step 1, draft, we enter the critical yellow node, critique step 1. The model acts as its own adversary, analyzing its draft for inconsistencies. This flows into a refinement node before ever reaching the final answer. This loop is the secret to bulletproof AI logic. Our first major implementation is the self-questioning cascade. What is this? It is a highly structured prompt where Claude actively interrogates its own initial response using built-in quality checks. The basics are straightforward. Claude generates a solution, but it isn't allowed to stop there. It must ask itself critical questions about that solution, answer those questions honestly, and then revise the work. Why is this so powerful? It automates the devil's advocate role. Instead of you having to manually read the output, find flaws, and write a second prompt, the AI does it all internally. How do you trigger it? You embed a command like, after your initial solution, ask yourself 3 critical questions about your approach. Answer them. Now revise. In our deep dive, this cascade actually simulates a multi-agent debate, but because it happens within a single API call, it drastically reduces latency while achieving incredible self-reflection. This state diagram maps the internal logic engine of the self-questioning cascade. We start by generating the initial solution. But instead of exiting to the user, we trigger the cascade, moving into formulate critical questions. The model then transitions into answer own questions, undergoing deep self-reflection. Finally, it moves to revise original solution, where it integrates its own fixes before arriving at the final optimized output. To push Claude even further, we use the multi-level analysis staircase. This framework structures recursive reasoning into explicit levels of increasing abstraction. Here are the basics. Level 1 asks Claude to identify the core issue. Level 2 explicitly commands Claude to question the assumptions it just made in Level 1. Level 3 forces a synthesis. Why do we need this? Because for high-stakes business or technical decisions, surface-level thinking is dangerous. You need the AI to uncover the problem behind the problem. How is it done? You continue the prompt. Level 4. Find the pattern between the initial and refined understanding. Level 5. Predict your blind spots. For our deep dive, understand that by explicitly numbering these levels and commanding Claude to reference previous ones, you are creating a rigorous chain. The tokens generated in Level 5 are mathematically weighted by the harsh critiques generated in Level 2, ensuring maximum analytical depth. Here is the multi-level analysis staircase visualized. Notice how it forces a downward progression into deeper abstraction. We start at Level 1 with the core issue, which feeds directly into Level 2, where we challenge assumptions. This leads to synthesis in Level 3, and then into Level 4 to identify meta-patterns. Ultimately, it bottoms out at Level 5, where the model predicts its own blind spots before finalizing the strategy. As powerful as recursive reasoning is, it has a major vulnerability. We must install circuit breakers to handle circular logic. What is a circuit breaker? It is a hard-coded validation check designed to stop the AI if its reasoning becomes trapped in an infinite or contradictory loop. The basics are simple. Recursive prompting can cause overthinking. The AI might chase irrelevant philosophical tangents instead of solving the problem. Why is this critical? Because it leads to context-rate state where the model becomes hopelessly confused by its own contradictory internal monologue. How do we build the circuit breaker? You literally append this to your prompt. Validation check if at any point the reasoning seems circular or irrelevant. Simplify the approach and focus on the core issue. In our deep dive, developers can automate this in code. Have Claude output its self-evaluation score as JSON. If the score tanks due to circular logic, your code pauses the loop and requests human intervention. Look at this decision tree for our circuit breaker. Every recursive reasoning step hits the validation check diamond. If the logic is sound, we safely proceed to a deeper level. However, if the model detects that its logic is becoming circular or irrelevant, it triggers the red node, the circuit breaker. This forces the model to strip away complex, confusing context and return safely to the core issue, rescuing the workflow. We must address the most dangerous aspect of this technique, the error amplification problem. What is it? It is the phenomenon where a minor logical error in step 1 compounds exponentially across the recursive loop. The basics are terrifying because level 3 relies entirely on the output of level 2. A flawed assumption early on guarantees a catastrophic failure by level 5. Why does this happen? LLMs are pattern matchers. If they make a mistake, their architecture pushes them to confidently justify and expand upon that mistake, rather than naturally backing up. How do we stop this? We require iterative refinement. You must instruct the model to verify its claims against source data before proceeding. For a deep dive strategy, use follow-up prompts specifically designed to seek inconsistencies. Ask Claude, are there any contradictions in the claims you just made? This forces the AI to actively hunt for its own amplified errors before finalizing the task. This flowchart vividly demonstrates error amplification. On the top path, a minor error in level 1 compounds into a flawed assumption, amplifies into a major error, and snowballs into a catastrophic hallucination. But look at the green node below, cross-reference verification. By injecting this verification step, we interrupt the compounding cycle early at level 2, destroying the hallucination before it can infect the rest of the recursive chain. For developers, we move from text prompts to programmatic implementation using tools like LangGraph. What is this? It is implementing recursive reasoning across a multi-agent coding framework to fully automate the logic loops. The basics involve splitting the recursion. Instead of one massive prompt, you use 2 AI nodes. One acts as the creative proposer and the other acts as the ruthless judge. Why is this superior? It isolates the generation phase from the critique phase, perfectly mimicking the advanced tree of thought methodology. How does it run? Node A generates a draft. Node B, often configured with higher reasoning effort, evaluates it. If Node B finds flaws, the code routes it back to Node A. In our deep dive, the secret is structured JSON. You force the judge node to output its self-critique as a JSON score. Your Python code reads that score and deterministically routes the workflow. You have just built an autonomous, self-healing AI system. Look at this programmatic architecture. The task input enters the proposer node, which generates options. These flow into the judge node for critique and scoring. We hit a deterministic code check. Is the JSON score greater than 0.9? If no, the precise feedback routes backwards, forcing the proposer to try again. If yes, the loop breaks, delivering a final validated output that has survived rigorous, programmatic scrutiny. Let us look at a real-time, high-stakes use case, strategic business expansion. The scenario: a CEO must decide whether to expand their product line or improve existing products. A basic prompt would just give generic business advice. Instead, the CEO deploys RCOT using the strategic decision spiral to force Claude to attack its own advice. Execution involves a prompt stating, Round 1, initial recommendation. Round 2, challenge 3 assumptions from Round 1. Round 3, integrate challenges. Round 4, project second-order effects. The outcome is incredible. In Round 1, Claude naturally suggests rapid expansion. But in Round 2, the AI is forced to critique itself. It realizes its assumption that expansion equals revenue completely ignored the company's operational bandwidth. The immense value here: by Round 4, the recursive loop forces Claude to adjust the strategy, recommending core product refinement instead. The AI corrected its own initial bias, saving the CEO from a disastrous expansion. This journey map tracks the strategic decision spiral. In Round 1, Claude provides the initial rapid expansion idea, highly confident but flawed start. In Round 2, the critique phase forces a drop in confidence as Claude identifies it is ignoring operational bandwidth. In Round 3, Claude recovers, refining the strategy to pivot to core products. Finally, in round 4, it confidently projects the positive second-order effects of this hardened strategy. To conclude our mastery training, you must internalize these best practices. First, aggressively monitor for hallucinations. If you see Claude's reasoning becoming contradictory or trapped in repetitive loops, manually break the cycle and simplify your prompt. Second, start simple. Do not use a 5-level recursion for a basic coding question. Match the tool to the problem. Third, and most importantly, rely on human validation gates. Recursive Code is the ultimate tool for deep exploration, but it is not absolute truth. You must validate the final insights using your own human domain expertise. Finally, use explicit formatting like XML tags to separate the draft, critique, and final stages, preventing the model from confusing its own outputs. Mastering Recursive transforms Claude from a static answer generator into a dynamic, self-correcting analytical partner. I invite all learners to like this video, subscribe to our channel, and visit quicktechie.com for premium certification prep, including massive Q&A banks, full ebooks, audiobooks, full-length training, and expert interview guides. See you there. Our final mind map summarizes everything you need for Recursive mastery. From the center, we branch into execution, relying on multi-level prompts and self-questioning. We branch into guardrails, highlighting the absolute necessity of circuit breakers and human validation to stop context rot. Finally, we branch into applications, showing where this shines best: complex strategy, agentic coding, and deep research. Master this map, and you will master AI reasoning.